Thank you for the introduction, Gauthier. And indeed, you remember right. That was the presentation I had done a few years ago now. Let me go full screen. Can you see my slides? Fine. Okay, I will assume that's a yes, that you can see it. Okay, so
yeah, let's
get started. So as Gauthier said, hi everyone, my name is Julien. I'm the extreme scale project lead at LightOn. So I'm leading a project on like building very large models and then putting them into use through an API for customers. The presentation I'm going to give today is about PAGnol, which is a very big French model we have built with 1.5 billion parameter. You can view it as kind of like a GPT-2 for French or an early GPT-3 of a slightly smaller size than the bigger one of 175 billion parameter. So LightOn, Gauthier introduced us briefly, but we are an AI hardware startup. So we are building photonic hardware, which is to say we are building chips that are not based on like classic electronics, which works with like, let's say electrons, but instead which work with photon, with light to perform computation, which come with a number of advantages. So we are based in Paris. We are a startup. We have like 20 people mostly. And we are very proud to have the first commercially available photonic processor, which is called LightOn Appliance, which is also available in the cloud, which we think is a particular thing for such an advanced technology. So today I'm going to talk about our endeavor into building very large models. And this talk is going to be kind of split in two, which is a first part that will be about like our effort to build the largest French language model and kind of like some details about this. And the second part about why do we think that what we call extreme scale models, so machine learning model with billion of parameters, are such an exciting direction of research, and why they are probably one of the biggest topics, I think, in machine learning research for the next decade or so, probably. So let's jump right in. So for PAGnol, kind of what started this endeavor is so all technology, or that's based on light, as I was saying before, works very well with large dimensions. So one of the biggest advantage of our technology over like classic electronics is that it handles very big dimensions much more nicely. And so we wanted to start looking at these big models like GPT that we saw, this extreme scale model, and we were kind of wondering, okay, where do we start? And we look at French NLP models, and we saw that there was no such models. There was no generative models, big generative model for French. All of the ones that there were, which had very cool names, were not of this kind. So we decided, okay, let's build one. That was roughly 6 months, 8 months ago, I think that this happened. And actually, in fact, to give a bit more of an opening beyond French, somewhat surprisingly, most languages don't have a model with more than 1 billion parameter yet. It's something that is limited to like currently French, English, Arab, Chinese Mandarin, and I think Korean, and I may be forgetting one more, but that's essentially it. So we have built PAGnol, which is a collection of 4 models up to 1.5 billion parameter. For the larger one, we have a quite large context size of 2048, which is much larger than what you usually see for language models like BERT. And what is very interesting, I think, is that a lot of people will come with the expectation that if we train a 1.5 billion parameter model, it's going to be super computationally expensive. But it turns out that this is not the case, because we use something called scaling laws, which I will discuss much more in the second part, which is one of the very interesting properties of these large models, to kind of inform the design of our training setup. And we end up only using 3 petaflops days. So for those of you that are not like super familiar with like the kind of modern jargon for computes, this is mostly as much as Camembert. So we train a 1.5 billion parameter model with the same computational budget as a model that is 10 times smaller, with a BERT that is 10 times smaller, which I think is quite interesting and shows that these very big models don't have to be super computationally expensive to train, while they are still more maybe intensive than some others and require some specific techniques. But the final computational budget can remain controlled at smaller scale. So, sorry, you may say, okay, 3 petaflops days, that's the compute, that's as much as a French BERT, that's fine. What about the data? Well, what we found is that we also don't need that much data. We trained our PAGnol on 24 billion tokens. So to give you an idea, you can divide it by 2 to get the number of words. So that's like 12 billion words. That's quite a few books, like a book's being like 100,000 words usually. So that's quite a bit. And what is very interesting to see is what is on the right, which I will come to discuss a bit further afterward, which is, if you can train a model, essentially the general idea of the scaling laws is that it's not efficient to train a model to convergence. And if you were to train PAGnol to convergence, you would need 162 billion tokens, which is a huge amount. But when you train only to some sort of what we will define later as optimality, we end up only using 24 billion tokens, which is much more reasonable. An interesting observation that we had as well is that when you train a generative model, you have to be very careful with the data. Like when you train a BERT, it's not going to be used for generative needs. So the data quality matters much less. But on a generative model, there is no room for error when it comes to the data. Like initially, we trained on Oscar, which is kind of like a common big data set for every language actually, but especially for French because the people that build Oscar are French. So it has quite a big following here. And we ended up with a model that was very naughty, to say the least, like very naive prompts led you to some very questionable answers. So we realized that we had to find a better approach for the data. But we still need quite a lot of tokens. So instead of curating our own data set, as has been done by quite a few people, we decided to take a different approach and to keep this automated. So we use something called Sissonet, which has been described by Facebook in quite interesting paper, which is a pipeline for extracting high quality data from a command call dump. And the general idea is that on top of the classic language identification and deduplication step, you have filtering that is done. And this filtering is based on a very simple language model that is trained on Wikipedia so that you only select data which has a quality that is similar to the quality of Wikipedia data. And this is a very good filtering because you only end up with high quality data. And this means the model will learn from high quality data only. And what I think very interesting with this approach is that it's quite scalable. Like this is not an expensive step. This can be done, and you can filter entire command call dump to obtain like hundreds of billions of tokens of very high quality data without having the need to curate your own data set, which is not always easy to do. If we discuss a bit about like kind of more the geeky stuff, the technicalities. So we have been training on the Janzé supercomputer, which is a French public supercomputer, which is one of the biggest supercomputers in the world. I think it's important to outline that this kind of project is only possible because of this kind of support. Like if you are not what we call, in French, we call them the GAFAM, but I think in English, you call them the FANG, like Facebook, Apple, Microsoft. And if you don't have like data centers with thousands of GPU at your disposal, you have to rely partially on national needs, on national like infrastructure. And it's very nice that countries such as France provide this kind of infrastructure to the researchers. So we are very happy to be able to work on this supercomputer. And we use, so in terms of like more like technical detail, we have been basing our code of Fescale. Also by now we have started diverging quite a bit, and we are looking into developing actually our own high performance library. Something we observed is that when you go online, a lot of library like PyTorch Lightning or even Hugging Face transformers or like a lot of them claim to support like high performance systems such as, like sharding or zero from DeepSpeed or the Megatron parallelism. But when you actually try to use them, it turns out that they don't. Like that it actually doesn't work well, that there is lots of issues, that hasn't been tested thoroughly. For instance, stability is a massive issue at scale, like the training of the models tend to become unstable, partially because of FP16, but partially because of other issues that are not quite yet understood by the community. And you realize that, actually all of this have to fall together. So there is a lot of work. It's not quite yet a turnkey solution to training big model. You have to work quite a bit. So we are based on Fescale, and we use sharding mainly, which is something like zero. So you split a section of the model and of the optimizer across the nodes. We use data parallelism, and we achieve roughly like 20 teraflops of throughput in this setup, which DeepSpeed Megatron in a similar configuration will reach around 25. So we are just a bit under. And the naive implementation, to give you an idea, would only achieve 3 to 5 teraflops of throughput. So it's a significant improvement to use the proper techniques for this. But this is where there is clearly a lot of work to be done in terms of engineering, in terms of making this actually possible. So as I said earlier, actually training big model is not that compute intensive, because once again, like, it's a difference between training to convergence or to optimality. When you train to convergence, you would end up with a budget of like 16 petaflops days for PAGnol, but we end up using only 3 petaflops days. So we train a bit past optimality, which is mostly the same as Camembert, as I was saying before. So this is quite interesting. And actually, in our collection and model, we always train on the same number of tokens. So our smaller models are trained to convergence because it's not that expensive, and our larger model are trained closer to optimality. One of the things is, okay, so you may ask, okay, we have trained this very large model. We had to do quite a bit of engineering to get there. What is it good for? So one of the things is that it's not good necessarily for fine-tuned tasks, as we commonly see. As you probably know from the T5 paper of Colin Raphael, fine-tune, like decoder only don't perform well after fine-tuning. So for instance, to be as good performing as Camembert, which is like a French BERT, we have to go to a medium model, which is twice as big as the equivalent Camembert. And it's kind of the same for, like, if you compare to Camembert large, which is a 300 million parameter BERT for French, we have to go to our large to perform as well. But one of the key things is that we are much more efficient in terms of compute and of tokens on which we train during the training. So like our medium model, which is comparable to Camembert in terms of end-task performance, only used up 0.7 petaflops days. That's more than 3 times less than the Camembert. So bigger models are more efficient. Like they are, like in terms of training, they better use the computational resources. And then there is obviously the fact that the generative capabilities of what we are of our model remain unique, and it's not something that that BERT can do. So we have an example in French that I will not attempt to live translate, but that is essentially a similar one to the one that OpenAI did a while ago with like the unicorn, and we can see that the model can come up with a fake news article about the discovery of unicorns, and that it's quite good. So if you're interested in training PAGnol, we actually have an online website on which you can train it. And if you are interested in just doing inference, we have a simple library to do this. And we have actually an API as well, to which you can provide access to commercial customers on which we are working. If you are interested, you can get in touch with us to discuss this. So kind of to summarize this thing on PAGnol, so we have built the largest generative language model for French. We found that high quality data is very important. And in fact, I think if you go a bit beyond this, and task specific data is important. So there is a good example of this, which is the work of LightOn, where they have been reproducing GPT-3, and they have been doing with a custom dataset in which they put a lot of code, like Stack Overflow dumps or that kind of stuff. And there are, I think, 6 billion model, like the 6 billion parameters model, outperform GPT-3 175 billion parameter model at like code task because it has seen a lot more in the training. So task specific data is important as well. As we will discuss just after, with scaling laws, we can train this model very efficiently. These models are actually much more efficient to train than their counterpart, like than their smaller counterpart. And we'll discuss this in just a bit. And this is just the beginning for us. We actually have been working on more languages. We have a Spanish model and an Italian model that we have built fairly quickly. Actually, once you have everything set up, it's we can churn out this model essentially. So we have an Espanol model, which is quite good, and we are working toward building bigger and in more languages. Like our goal is to target as many languages as possible, because, as I said, once you have the infrastructure to train them, it's quite easy to keep going. I will answer live a question I see about Copilot. Copilot, which is an OpenAI recent thing in cooperation with GitHub that builds code. Copilot obviously outperform the LightOn GPT or the GPT-3, even at much smaller scale, because it is custom built for code. And a large part of what they have done in the Copilot paper, it's not just the fact that you only train on code, but it's the fact that they have some sort of specific training regimen for code, where it's like code exercise that the model has to solve. And they find that if you just use auto-regressive training, you don't get as much performance than if you add this kind of like problem-oriented, problem-solving task in the training. So copilot is obviously better than this and this. But I still think it's fairly impressive if you look at GPT the 6 billion GPT model of Later AI. I tried some code stuff with it, and it's honestly fairly impressive that a model that is targeting like English language can be this good as at code task. I think it's quite fascinating. So, okay, to go a bit broader, to kind of extend a bit the horizon, I want to give a bit of an overview of what I think are some of the most interesting trends in very large model and why they are so interesting to study and why I think it's very worth it to expand them. So firstly, the thing is that these big models are happening. That's a very simple observation, but if you look at the count of parameter in the NLP models or at the cost of training of machine learning model, you can see that there is roughly a 3-4 months doubling time on both sides. You may notice that we have been a bit on the plateau recently. I will discuss this at the very end. But yeah, and essentially recently we passed the 200 billion scale with like Pango Alpha, which is a Chinese model from Huawei. But the training is still like the king in terms of training cost is still GPT-3 because GPT-3 was trained for much longer. So clearly a lot of people are looking into these big models. And this is not just like kind of like an academic, dream of like, oh, let's just spend millions of dollars on compute and have fun. This is also coming to the real world, to real world application. So GPT-3, for instance, generates 4.5 billion words per day for customers. This is enormous. To give you an idea, that's 50,000 books per day. And across an entire year, there is only 100,000 books published in French. So every 2 days, GPT-3 writes more text than there is French books published in a year. And French is one of the languages with the most books published every year. So this is fairly insane scale of use. And you are seeing a lot of startups and a lot of companies appearing, targeting research and API for these big models to bring this to the industry, and also hardware startups that are looking at making hardware that can handle this kind of like crazy large models. So, and it's not just NLP. This is something I added very rapidly yesterday, but we also see this with proteins. So we had AlphaFold recently, but there is also ProGen and ProTrans, which are very large models for protein data, which have achieved state of the art in some tasks. We also have computer vision with image generation with DALL-E, for instance. So it's not just NLP. We have actually been tracking at LightOn the progress on this. We have a website called Academicon, which is tracking like, what are all of the models that exist beyond 1 billion parameter? And it's kind of like a leaderboard if you're interested in having a look at what the playing field look like. Like, are people using more TPUs or GPUs? Of which framework are they using? Which nations, like kind of which countries are furthering this thing? So if you're interested, we have this website. Okay. Why these models are so interesting? Well, it lies on something called scaling laws. So if you have a background in physics or in engineering, actually, you may have heard of scaling laws, which are like scale invariant, which is an effect of scale invariant properties, which will give rise from very complex phenomena, which are very hard to describe, like the ECS, the Earth circulation system, the entire atmosphere of the Earth, like finite element simulation of very complex behavior, like an explosion in a tank, like a flame for a rocket, like for Jeff Bezos' flight, for instance, yesterday. Very often, it turns out that, you have this very complicated numerical simulation, which is very hard and to generalize. You can bring a scale invariant formulation and end up with a very simple scaling law, which will describe the phenomenon at tremendous scales. And there is a lot of them. So one of the questions we could ask is, can we get something similar for machine learning? Because in engineering, it's super useful. Like, it's a way that you get kind of a back of the napkin estimation of kind of anything that you want to do, from building a plane to like building a skyscraper. The thing is that currently in deep learning, we don't have this. Deep learning theory has been quite disappointing in a way because it's not a good predictor for what is actually happening, and it's not really useful to practitioners most of the time. But there is this paper from OpenAI that came actually before GPT-3 called Scaling Laws for Neural Language Models, which if you haven't read, it's a very accessible paper and it's a very good one. And they make this observation. So they are training very large GPT model, very large language models. And they plot the test loss against the compute used for larger and larger models. And what they observe is that there is kind of two phases to the training. There is a first phase with a very sharp decrease of the loss, like very efficient training, like the loss is changing a lot for compute that is changing very little. And then there is very inefficient convergence. So the idea is that, okay, you have like, if you look on the bottom left, you have kind of a line that describes like a Pareto optimality frontier, like the optimal compute frontier. Like if you're at this given compute, you will want to train a model of this size. Like that's the best you can get, like of the green size. And you always want to stay. The idea is that you don't want to train a model to convergence. You only want to train it in the efficient part, and then you would open to a bigger model. So this bigger model, because a bigger model will perform better, will learn faster, like it's more efficient. From each sample that you show to the big model, it will learn more information than a smaller one. And they will generalize also better in that they will show new capabilities such as few-shot learning. So I will not go too much in depth into this because, but the general idea is that you can derive precise laws, like very simple scaling laws that will predict, like at a given amount of compute, you will get that kind of performance and you will need that many tokens and that many parameters to be optimal. What is very interesting is that this is very easy to reproduce. We have reproduced this with a completely different code base from them in a different language in French, and we obtained very similar exponents. It also shows that like GPT models or transformers in general are fairly architecture agnostic. That is to say that you can arrange the parameters however you want, essentially. All that matters is that the parameters are there at the end. And this is also something that's not just true for language, but that's true for like computer vision videos, mathematics, even like different domains like code or whatever. Like it seems to be something that is generally true that you can derive scaling laws. And it may not be unique to transformers. There is some research recently on this. And this links to a text that I think is very interesting, which is called The Bitter Lesson from Sissonet, which is that the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. So the key idea of all of this is that once you have a good prior that is scalable, all you have to do is make it bigger to go towards more and more capable model. And I think this is what we are seeing happening with transformers right now. So to kind of conclude this talk, I will give you like a few of the direction of research that I think are the most exciting about extreme scale models. An analogy that I like to make is, I don't know if you are familiar with the movie Arrival, which is a movie in which aliens come on Earth and essentially a linguist has to figure out their language, which is really hard because they don't think like us. And I think there is a parallel with research in extreme scale models in that we are capable of building models that are much bigger than what we actually can understand scientifically. Like we don't know yet what are the full capabilities of this model, and we still have to study them. And here's a few examples which I think are very interesting. First, there is a classic one that GPT-3, for instance, can learn new tasks on the fly. Like just you show new tasks and it will learn from just a few examples, even like coding an interface, for instance, which I think is really impressive. Then there is something called prompt tuning, where instead of fine-tuning the model, of fine-tuning like the 600 gigabytes of weights, which is not really tractable for a large model, you only fine-tune like at the beginning of the prompt, kind of like a few words. Like there's a few words, and it's not that you choose them, it's that the vector representation, that is what you fine-tune, that is what you do optimization on. And what you find when you do this is that actually at around 10 billion parameters, this very simple prompt tuning, which is just a few kilobytes of parameters, outperforms old school fine-tuning. So this is putting into question the classical fine-tuning paradigm that we have in NLP, for instance. And we have reproduced these results at LightOn with the PAGnol model, and we are seeing a very similar effect. Actually, we are seeing an even stronger effect because this is done on a model that is like T5, that is an encoder-decoder that is modified to do language modeling afterward. But this is on the GPT, and we think that on GPTs, actually, prompt tuning is much more competitive. It works even better. So at the 1 billion scale with GPT models, we are already seeing that this is competitive almost with fine-tuning, that you can just fine-tune a few kilobytes that you can prepend to each sentence instead of fine-tuning the entire model. There is a fact also that when you go at scale, the architecture doesn't seem to matter anymore. Like there has been very exciting results with GMLPs and with mixer architectures, which are architecture that doesn't use attention, but only MLPs. So it seems like at scale, essentially, it's only the number of parameters that matter. And there's open questions like, how do you steer this model? These models are very capable, but sometimes they fail, and you don't really understand why. If you have tried GPT-3, you have seen this. Another example is like image generation. So this is like VQGAN, which is a classic model steered with CLIP, which is a larger model trained by OpenAI. And what you can see is that when you put the words Unreal Engine or trending on ArtStation in your prompt, you end up with much higher quality results, like with a result that look more like art. And this is just because you have prompted a proper direction. How can we control this better? And this is an open question right now that is especially important for fairness and ethics, which is very important. And one last thing is the question kind of how sustainable are the current trends. So firstly, there is the issue of, okay, this is mainly done currently by like OpenAI or maybe Google or whatever. So there's currently in France a project that has started, which is called Big Science, which is a huge collaboration across actually many countries and many institutions, where we are more than 500 researchers that are going to use the Jean Zé supercomputer I was talking about before to build the largest language model ever built. It will be multilingual. And it's an experiment in a novel kind of cooperation across many, many researchers on building very, very large artifacts, kind of like the LHC. And this is very exciting. If you're interested in contributing, this is like an open thing. So you can go on the website and you can see all of the detail to join us. So one step that I think is very interesting to kind of circle back to what we do at LightOn is if you want to build very large models, so research is completely public. So engineering can be challenging and is not to be underestimated. But the thing is that you can find very experienced engineers quite, I will not say easily, but you can find them. So real bottleneck is the hardware. And an interesting, I think, thing is to look in the future. Like, let's look in 2025. Let's imagine that we have hardware that is 10 times better than the A100 today. And by the way, this is like a terrible overestimation. We will not have in 2025 GPUs that can push 750 teraflops. This is me being very nice to NVIDIA's engineers and their work. Okay, what can we train with such a large system? Like we have 15,000 of these amazing GPUs in 2025. What can we train? GPT-3, 175 billion parameters, can train in 7 hours. A 1.5 trillion parameter model in 1 week. A 13 trillion parameter model that would be 100 times as big as GPT-3, that will take you half a year. So essentially, let's say that this is a limit. So in 2025, we will only be able to go 100 times bigger than GPT-3. Like we are kind of stalling, and you have seen this in the curves that I've showed you earlier, like we are stalling in terms of progress because we are reaching the very limits of our hardware. And the current trends like that we have, if you want the current trend in terms of scaling to be sustainable, we will need a 1 quadrillion parameter model in 2025, which you can see from this slide is not going to happen. And by the way, 1 quadrillion is also mostly the number of connections that we see in the human brain. So it's mostly an equivalent, very worse, very, very worse as well. So it's mostly where you would want to go as well with the current trends. But this is not happening. So we have to think of new, essentially paradigm for hardware and for how we train these models, because these trends, if we want to keep pushing for them, we have to find ways to make them more sustainable. That's pretty much it. I hope you were interested. If you're interested in PAGnol, in very large models, and what we do at LightOn, you can contact us. And if you're interested also in internships or that kind of stuff, we are also always happy to host interns in our extreme scale team. So if you're interested in working on this kind of problem, you can also email us. That's it. And I can now answer your questions.